Alrighty, folks. Welcome back. Hope everybody had a good Thanksgiving break. Had some time off and ate some good food or relaxed. Hopefully not too much homework, those kind of things. Let's see. So just going to kind of get us started here. And for today's warm-up, I wanted to show something cool or hopefully inspirational. And again, maybe for folks still thinking about a final project, we're trying to solidify an idea. This particular YouTube channel might give you a few ideas. It's a really cool one. It's called 2-Minute Papers, although they're not always 2-minute presentations. But they talk usually about papers that have been presented in computer graphics and usually from the SIGGRAPH conference, and try to give the sort of 2-minute demo or high-level overview of the particular topic. So I think it's just one of the nicer YouTube channels because it's taking very complex subjects and trying to boil them down to what the key idea is. And that might be interesting for folks in this class to look at if you're particularly interested in geometry or doing something with AI or image processing in your project. So it might be a nice place to look for some inspiration. Just wanted to share that with folks. So with that in mind, let me go ahead and move us to our logistics here. And so last lecture before we headed off for our holiday, we were talking about two topics really. A new way to render geometry, or at least a new primitive, that is the triangle strip, and how we use that to render terrains. So again, using some of our tools here and learning about also height maps or height fields. So again, using textures, which we've used this time to store height information and apply that to our triangle strips and render a terrain. And then we talked about how to start organizing our scenes with a data structure called a scene graph or a scene tree. And basically the idea that we need to, or that we can rather, organize all of our 3D entities, I'll call them, whether they're lights, 3D objects, transforms, or whatever, into some tree structure. Okay, and then we can sort of apply things down the tree. And you can be quite granular with that. You could even have shaders, for example, as part of your tree and sort of group things. That's not what we've necessarily done in the sample code, but again, you have full granularity with that data structure. So that's what your homework 6 is about, and you'll be building a little solar system to practice with transformations and using the scene graph. Again, homework 6 tends to be a little bit of a shorter one, so feel free to get started with that at any point. And as you know, homework 5 is due very shortly, or very soon, tonight, anywhere on Earth. We should have some time after class to help debug that assignment if anybody needs some additional time. Otherwise, there are office hours tomorrow as well. And just to sort of give us a idea of where we are in the class here, so we are at week 12 here. Next week we will meet here as well and talk about what's going to end up being shadows. I might talk about geometry shaders and some other topics, but I think I want to talk about shadows. I think those are pretty cool. There won't be a lab for grading because you'll have enough on your plate with the final project, but I will have some sample code for doing a simple shadow, just so you know how to do that. So sort of schedule-wise here, you should probably be, thinking about after today, especially, or once you get your assignment 5 wrapped up, hopefully you have a project idea selected and maybe at least one resource for that project to help you along. So if you're doing particles, maybe you found a particle tutorial. If you're doing something with geometry, hopefully you have some resource to help you, whatever it might be. If you don't, please come talk to me at some point today. I'll try to help give you some resource for your project, so then you can start working on that as needed. Let me pause there and take any questions on logistics from folks. The one logistical thing I am still figuring out is what we're going to do on the 14th module here for our final projects and wrap-up, whether we'll be in class, whether we'll do that online, or what sort of makes sense. I might poll for that. Technically, our last day of class is, I think I was looking, it was the 9th or the 10th. For our sort of final wrap-up, we'll figure out what to do. Very, very, very soon. I'll send something out. I know some folks are already flying out of the country and that kind of stuff on the 13th. They've let me know. Any other logistics or things blocking folks from making progress that I can help as a group handle? All right. If not, let's go ahead and dive into our next module here. And talk about buffers a little bit. So again, one of the great ideas in graphics programming, or at least modern graphics programming, this idea that we're populating buffers with information and sending that information off to the GPU. Okay, really it just comes down to two major ideas. It's a little bit boring if you think about it this way, but graphics these days is all about what you can put in a buffer and send to your GPU, and then how you can write these programmable shaders, right? And we've talked about these a little bit. We've used these terms, vertex buffer, index buffer, or element buffer before. That's how we've been creating our geometry in assignments 3, 4, and 5 for the model loaders. So again, we're getting familiar with this idea, and hopefully familiar with this pattern of what OpenGL is. Right, this sort of old C-based API where you create objects by calling various C functions that generate an object, and then you populate it with some attributes, and then you bind to it when you want to use it. Sort of repeating that over and over and over again. That's the idea. So we're going to focus a little bit here on a different category of buffers today, and those are known as screen buffers. Okay, and they're actually not anything really new. We can actually go back to assignment 1, right when we had our PPM images, and that's a buffer, right? It's just some collection of bytes that represent the colors of an image, right? All the different pixels. So we've looked at that previously. We looked at that with our software rasterizers, where we had a color buffer that we were drawing out to. And we've talked about depth buffers as well, depth buffer or the Z buffer. That was the buffer that just, it was a collection of bytes, 1 byte per pixel, indicating which fragment was closest to us and which one would be drawn. Now there is another type of screen buffer we haven't talked about, the stencil buffer. I'll give a little introduction to that. That one will actually be a little bit more interesting when we talk about shadows, and maybe I'll talk about reflections a little bit. But there are many types of screen buffers, and these are the 3 that you always have or have by default. Okay, again, so just to look at this, here's an example color buffer. It's a image that's colored here, so we can see that. Again, it's just some format, whether that's holding the red, green, blue values, maybe alpha values, maybe it's some other format. If you actually look through OpenGL, there's hundreds of different color formats that could be stored. But the idea is you're holding your color information here. And then there's the depth buffer, again, which we've looked at. And here's a rendering of it. Again, the darker pixels indicating that they're closer to us for those particular objects, and the lighter color farther away in this image. Okay, and here's another rendering of it for reference. All right, and then there's this new buffer that's always been with us, but we just haven't talked about, but you should know that it exists. It's called the stencil buffer. Stencil buffer, if you've ever heard this term of a mask, or maybe you've done something in Photoshop where you've sort of masked out and hidden or erased part of an image, that's essentially what the stencil buffer is used for. So you have your color buffer here on the left. Then on the right side, you have your stencil buffer, which is typically just zeros and ones. Anywhere that there's a 1, you keep that fragment, and anywhere there's a 0, you discard that fragment. Okay? So what folks will sometimes do with stencil buffers, or why they're sort of interesting, is that you can, one, it's a way to sort of filter out part of your image, but you might be able to save a copy of this image or part of it, maybe this little box here, and then have some reflection or maybe some shadow cast from just these particular fragments. So that's the idea of where it's sort of useful. It's not always immediately obvious why you'd want to render your scene like this. So we'll have to look at an example. I think we'll see it when we do shadows next week. All right, so for each of these screen buffers, we're just storing a collection of bytes. Again, we can see that clearly in the stencil buffer in the middle rendering here. And what's really kind of interesting, or what makes screen buffers interesting, is how we're going to be able to compose some of these together. So meaning I can have, a color buffer, that's kind of interesting. Maybe I can do something then with the depth buffer. Well, we are actually using that anytime that we perform the depth test. But we've also seen, in a way, sort of other uses of collecting bytes together in some buffer, with our textures. And we've seen things like normal maps, so and how we sort of compose those together to make something interesting. So the good news is, with OpenGL, is it allows us to create our own screen buffers that we can do something interesting with. And I'll try to give a few examples of that today. All right, so what we're going to be talking about, and we're going to be diving into, if you're following along on the Learn OpenGL, the resources in every module, we're going to be diving into the Framebuffer section. So this is part of the advanced section of OpenGL, which is kind of where things start getting really cool and interesting, and we're trying to figure out neat hacks to draw things. So frame buffers. All right. So what is a frame buffer? And this is another type of object. I'll give a little caveat with frame buffers, but it's basically some object that we can render or draw to. Right? Somewhere where we can store fragments or pack some bytes into, some buffer. And here's a little bit of an illustration of what a frame buffer is. You can kind of see it on the left side here of this particular image. And you'll see that this frame buffer is a collection. If you want to imagine this like a C or C++ struct or a class, it's basically got a place where you can attach a bunch of color buffers. So like the color buffer that we've been drawing to has a depth attachment. So you can have that depth buffer, and you get a stencil attachment as well. And in fact, I can have multiple color attachments to these, but this is just sort of the idea. So this frame buffer is going to be the thing that we're just going to sort of compose a bunch of different buffers and then finally draw out some image from our frame buffer. Right? The frame buffer, if you recall from our OpenGL graphics pipeline, that's the last step, right, where we draw from our fragment shader out into a frame buffer. All right, so just to illustrate that, right, here's the picture. So drawing your attention to the bottom right, we start with our data. We create some OpenGL objects. Those get shipped to the graphics card. You run your vertex shader, fragment shaders, and you draw everything to the frame buffer. That's what we've been doing this whole time. All right, now, the cool thing, or what this is going to lead us to by the end of the class, is once we can access the frame buffer, which has all the pixels or fragments that we've been drawing onto, well, if that's just a collection of bytes, we can actually do some post-processing on those bytes. So if you've ever wondered how to do like different filters, or have ever messed around with filters on, say, Instagram, or these kind of things, That's the way that we can get some interesting effects. This is just again, a collection of bytes, and we can modify those as we need. All right, so that's a little introduction to Framebuffer objects, or what we're going to be talking about. But I think I could probably summarize this lecture in one slide and tell you that a Framebuffer is like a PPM image, and we sort of get that. But I think a way to maybe see the power of it is to look at some real applications and see how these Framebuffers are used to compose interesting scenes. So I want to show you this really neat study here. Actually, there's a couple of them. I'm going to show at least this one in slides, and maybe we'll dive into another one. Again, just to show you what's sort of possible, or if you've been wondering, like, how do real-time applications get really cool images, to say. So anyway, the credits go to this gentleman, Adrian Courage, who does these graphics studies. And basically what he does is he goes to a graphics debugging tool and just grabs a frame of whatever is being drawn to the scene. What he's grabbing is the actual frame buffer, and the frame buffer has a bunch of these attachments. So he's picking out the depth buffer, and the color buffer, and all these things you can see in a graphics debugger. Okay, and then we'll be able to see all the individual buffers that go into just one rendering of the game. All right, and he tends to do these for sort of action games and these kind of things. So I have one here, Doom, sort of a classic. So let's just go ahead and dive in and take a look here. Maybe we'll look at one or two of these to see what's going on. And to start, what's sort of interesting is with the Doom game, they actually only do one texture load in the entire game. So we've been loading, well, at the most 2 images, whether it was our normal map and our whatever other diffuse texture map, or we saw the brick wall and the grass in some of our labs. But in the Doom game, they actually just have one what they call a mega texture here. You can actually look at it. I've linked it here just so you're aware. The Doom 3 source code, which is the newer Doom's built off of this, but you can actually look through the Doom source code. It's open source, which is a great place to learn how things are done. And if you actually magnify into this, you can see there's 16 times zoom in on these textures. They're several gigabytes large. You can see the actual details. Right, and we know how to use our fragment shader to sort of sample individual pixels here. So anyway, that's the first sort of stage here. One question or one thing to think about is, why do they go through the trouble of making this mega texture? Anyone tell me your thoughts? Why would that be more efficient? Thought here and then here. Yeah, right.
I was thinking because maybe it just, especially maybe in older systems, it might take a while to do that file input-output, and so just doing it all in the game saves time.
Yeah, on the CPU side, right, it takes time to see. Yeah.
If you have a bunch of oddly shaped textures, you can sort of puzzle them together in the mega texture to save space, so you don't have a bunch of rectangular images with useless data.
Yeah, right, it can be a little bit more compact. Let's see if I can, right, if we have a bunch of, this is sort of the classic bin packing problem, right? The problem I always tell people Amazon really cares about, right? How can you store a bunch of packages? But yeah, just some shape like this, another puzzle, some other shape like, I don't know, maybe a bunch of circles or something, right? We can tightly pack these together if you have a bunch of, wasted space here. That's exactly right, yeah. So both, right? We're more efficient, so we have more room on our GPUs, and we do less seeks on our CPU, right? We don't have to fetch data, seek for all the data over and over again. So this was sort of a revolutionary idea around the time that Doom 3 came out, which was in the early-ish 2000s. And now this is sort of a standard. The other name, texture atlas. So atlas is like a map where you look things up and you find all your textures there. And then mega textures being just something huge like multiple gigabytes, where you have all of your data. All right, so all of your data's in the GPU, or as much as that you can pre-compute. Okay, so that's sort of the first step in our process. And again, we're thinking about frame buffers for today. So blocks of pixels. So these are all your, again, diffuse texture maps and those kind of things. Now, and some of the other things that may or may not be in that mega texture are any light maps, so any pre-computed lighting. I think we just briefly touched on this idea that you could bake in what's called a light map or pre-compute your light for a scene. So Doom, for example, uses this technique here. Now, I think in this particular case here, they're actually computing the depth map for each of the objects that were loaded in the scene and just making one texture from those. Okay? Because somehow they're going to use the depth information or how far away some fragment is to, again, enhance what their scene looks like. Now, some additional types of buffers that screen buffers that you might want to store that we wouldn't immediately think of are things like velocity maps. So what this is showing, this character here is sort of jumping out of the screen from the left side of the window to the right, and that's being captured in this map. So the X, Y, and maybe Z positions are being stored as RGB values here. And basically what this is used, if you know the velocity or the direction that some object is moving, you can apply a blur to that portion of the screen. Okay, so here's sort of, is the map where you can see the actual rendering of what's being captured and encoded in a texture. So same sort of theme that we have here. Here's the effect that it's trying to create, though, if you're not familiar with the term motion blur. So on the bottom here is just no motion blur, and on the on the top here is with motion blur. So again, if you're like moving your head really fast, looking at the ground, it should look something like the top, there, where things kind of get out of focus here. Okay, so we can use this velocity map for just this character or this part of the scene to sort of blur them because they're moving. Okay, so here's the depth map, just the rendering, again, of the same scene here, so you can see the different pixel colors, again, to understand which fragments are far away or which ones are close. And then some other of the maps here that have been computed, or pre-computed. So the normal map, which we know some artist has created, and then also the specular map. So we didn't implement specular map. This actually might be an interesting thing for folks to think about implementing. Basically, it's a grayscale image, just like our height maps. The more light a texture is on your specular map, the more shiny it is, or you increase your specular effect. Okay, so those are all usually pre-computed. All right, so this is all the different buffers, whether they're textures or something that's computed, and the actual frame that are being put together. In fact, there's a lot more, so we're actually going to jump into the web page so you can see, all the things that are put in to make the final scene here. So just to give you an idea, again, it's a little bit scary, sorry. But the left side is with no effects being shown versus the right side. So you can see sort of the difference it makes on the different materials or as things are applied. I think actually on the left side there's still some specular maps and stuff, but quite the difference. So I actually do want to because we'll have time today, click on this study just to give you a little bit of inspiration on two things, actually. Let's see. Let me go to this and this. I'm going to sell you maybe one final project idea, but first I want to look at this. So you can see, how a frame is rendered. Again, this is sort of the final scene here. A little bit of discussion about the mega texture update. So how they just store everything there. The actual shadow maps, they're using some of the depth values, which is pretty cool. Here they're doing a few pre-passes here. I'm actually not 100% sure what this is. They might be doing some other computations here. Let's see. The velocity map, which we saw. Sometimes we want to know if an object is going to be occluded or blocked by something. Right? If some object is blocking the other one, that means it might be casting a shadow on it, so you can sort of darken that object. So that's what this sort of little box test is. Here's just applying the lighting, so you can see here. And they're talking about how the camera works here, which we know about the camera frustum. Let me go through here. The different maps, normal map and specular map. This is a topic that I'm saving for the last day of just other things you should probably know in graphics. SSAO, screen space, ambient occlusion. So this is figuring out in screen space, looking at pixels, trying to compute where some shadow would be. Okay, so then we could see some of the things being combined here. So again, this is just part of our frame buffer. And they show some of the different reflections. And they're starting to put things together. I'll let that play one more time here. You can see where they're adding fog at the end. Some more lighting effects here. And this is all going on in every single frame of the game. It's kind of fascinating. What's going on? Some transparency here. Let that play one more time. And a whole bunch of other things here. Up here's the motion blur. Let's see. See if it. You can kind of see over, this gentleman's head here. The blur. Guess they're moving. And then bloom, sort of a effect. If you had a neon light or something and wanted it to really brighten up. All right, then a couple other effects here. All right. And then at the very end here, they are actually doing some post-processing on the actual. Again, this is your Instagram filter at the very end, where they're applying some film grain or some sort of just sort of effect at the end. All right. So let me show you one more of these studies here. Because I think it's kind of interesting to look at some of these graphics applications and just see, what are the different effects? How do you compose the final scene here? Okay, this is from a game, Deus Ex. Let's see. So you can see the normal map here. All right, so we're familiar with those. So you can see the depth map. And they are actually computing shadows here. Here's my scene. Let me Let me give you a moment just to study this for a moment. Now our character is looking at this sort of centerpiece here. Question for folks here: where are my light sources in this image, or where is light being cast from? Yeah. Okay.
Have the ring at the top.
Yeah, ring at the top. Yeah. There might be some other ones, but this is the immediate one that I see here. Maybe I can't tell if this is. I think this is a light source here. But just to sort of preface, so the way that we compute shadows, and again we're going to talk about this next week. Notice we're sort of looking top down where that light source was. So whenever you're computing a shadow, you're rendering your scene from the light's perspective. That's how you figure out where a shadow is going to be cast. Okay, that's why this is sort of a top-down scene. So they're doing this shadow map here. And then this is sort of a mask or a stencil. Again, figuring out where the shadows are cast. This other sort of technique I just mentioned in passing, SSAO, screen space ambient occlusion. Sort of finding out where your edges are, and usually on the edge of a surface, some shadow is cast, so you can kind of see those a little bit more clear here. It's almost like a edge detection. If you've ever seen that, or if you've ever put your portrait in an edge detection, or you just see like the outlines. All right, and then they're actually storing those values and combining it with the normal map here. All right, here's your light. This one's actually kind of cool to see. So they're putting in lights somewhere in the scene here, and you can see where they're actually being cast, those objects. Okay, and then they're saying forward rendering. Okay, this is where the actual rendering happens. In the order of how all of these, we have all of this information, our normal maps, depth maps, all these things. So it's these 5 things, or at least the 5 that are revealed here, that are being composed to build the image here. Okay, so I'll let it just kind of run through a few times. All right. And then transparency is almost always, I shouldn't say almost always, but most of the time handled at the end. There's some sort of globe or something here in the middle here. All right. Here's that bloom effect. Again, objects that are emissive, like a neon light, a lightning bug, or a firefly, depending on where you're from. Sort of that can emit light, would have some sort of light here. All right, so you can kind of see the before and the after. Here's your emissive source. So again, if you have some sort of texture map or want to play around with those specular maps and sort of exaggerate the fragment's color, that would be one way to implement a bloom. Okay, and we haven't really talked about anti-aliasing, but it's a way to smooth out lines so that they're not as jagged. All right, so I think we kind of get the idea here. Let me go. Let's see. The user interface, that's okay. All right, so that's kind of cool. There's a bunch of these other graphic studies, so I'd encourage you to take a look at them. Actually, what's really nice about them, too, let me go to the very bottom, just to give you a little bit more inspiration on the further readings. You can usually see, well, you probably can't see there, maybe we can see now, but they'll have the GDCs, the Game Developer Conference, but that's where the actual talks will be, and the developers will tell you, how did they compose and actually render this scene here. And they'll have a few other links. The Doom one actually has a lot of other really interesting links there as well. All right, let me sell you on one final project that'll sort of that I think is a good one, especially if you're watching those graphic studies, you're like, this is pretty cool. How do you compose all these things? And you want to sort of start thinking like a graphics software engineer at sort of a gaming company. The deferred shading topic on Learn OpenGL is probably where you'd want to look. But this is following the same idea where you have a few different screen buffers and you're computing these every frame, maybe using positions, normal maps, specular maps, an albedo, or just a diffuse, and then combining those all at once. So it's called deferred rendering because you're deferring or waiting to render until you have all that information collected, your normal map, depth map, position, normal, specular, etc. And then finally combining or composing all those buffers together at the end. All right, so that's the idea there. Let me pause for questions. Any questions on these graphic studies? Or anything interesting that captured folks' attention? Yeah, take a look at it. It's pretty cool. All right, so back to frame buffers though. Get this full screen. All right, so how do we actually use this frame buffer to create something cool like that, right? We need to be able to create more of these buffers that we can render into. All right, so our goal is going to be to be able to render something that we're capturing from our camera into a separate texture. That's one technique that we can use. Then the second is, which is what we're going to end with and what you're going to do in the lab today, is once you have things in a texture, well, that's just, again, pixel information, and you can manipulate pixels as you like, right? Just like what we did with the PPM image where we lightened or darkened the pixel data. Okay, except the difference is we're just going to do that in the fragment shader and do it every frame when we're rendering. All right, and this is my warning where most of the internet tutorials sort of break down here. But I'll try not to fail you. So, how do we generate a frame buffer? Well, again, it's going to look a lot like what we've been doing with our other OpenGL objects. We're going to call, generate, some sort of generate function, and then bind to the frame buffer, and then eventually delete or free it. Okay. Now there are a few other steps. So hopefully I'll give you a good framework here for getting a frame buffer up and running. But the other sort of magic thing, or the thing that I think is interesting, is that we're going to do all of our rendering from now on, for the last 2 weeks here, to a single quad. So you're not going to have any polygons in your scene. You're not going to have any information. You're just going to be rendering a single texture that is our frame buffer onto a square. Okay, and that square is going to cover the scene. Okay, so hold that thought. I'll show you how it's done and give you a little bit of a demo. All right, so for today we'll have a frame buffer abstraction that'll be part of our lab. And this is going to be a new class that we'll have here. So here's sort of our interface that we'll be working with. So I just want to give you a little introduction to that. Our frame buffer's going to have a custom shader. So today we're going to be working with 2 shaders now. We're going to have the regular shader that draws out, you're going to have your own vertex shader and fragment shader, just like we've always had for our geometry that we're rendering. But then you'll have a second one for your actual frame buffer, which is just acting on the actual screen. Okay? So for our frame buffer, it's going to have its own shader here. All right. The constructor's job is going to be to set up our actual frame buffer. So again, in our frame buffer, it's going to have its own shader. So we've got to load in some shader here, create it, and then there's going to be, well, you can see at line 22, we set up a screen quad. So again, that's just going to be some rectangle that's drawn to cover our screen. Right. Then when it comes time to, after our constructor, at least in this interface, you could change it how you want, but we'll call create. So create our frame buffer. And that's going to look something like this. And the code's a little bit tiny to read on a slide, but you'll have a glgen frame buffer function. You'll bind to it. And our frame buffer itself, since it's storing pixel information, needs to store that somewhere. So we're going to have a texture that we're drawing our pixels to. Okay, so you're immediately going to see after we generate a frame buffer, we generate a texture. Then we go through the sort of binding our texture, setting up some texture parameters, and so on. And then there's a sort of strange function, which is highlighted here on line 3, geo frame buffer texture 2D, and we're attaching to our frame buffer this texture. Okay. So again, it'll look something like this. We have our frame buffer object that we create in OpenGL, and then we are attaching to different screen buffers or collections of bytes, different buffers. Right, here's a texture object, and it stores pixels. Okay, and that makes sense. It's going to sort of, we're rendering on top of our screen color information, so we need some place to store it. All right. And what's the rest of this code doing when we're creating our frame buffer? Well, we're actually, again, drawing to it pixels. And that's stored in something called a render buffer. Okay? So there's a little bit of a lie here in the term frame buffer. If anybody talks about it, it's not actually a buffer. It's just sort of a data structure that points to a bunch of things. Okay, it doesn't have an array. It doesn't actually store pixels. The abstraction actually looks something more like this, where there's a separate render buffer here. Render buffer. And this might actually point to the texture object. Okay, so that's just a little bit of an aside, but you have an example to see how it's set up. All right, so we have this frame buffer. Where can we actually use it? Well, we have a render abstraction as well. So in the support code, we have a separate renderer class. And this abstraction is, in a way, it's set up so that you could use this or see an example of it if you wanted to use Direct 3D later on. You would have different renders that you could sort of plug in. You could plug in your actual software renderer at some point if you had other features. But the idea would be you'd have a renderer here, and then any number of frame buffers would be part of that. All right, so as we saw in the example with Doom or in the Deus Ex game, right, you're going to have velocity maps, depth maps, color maps, shadow maps, all these sort of things here. So you might need multiple frame buffers. Okay, so you're going to have a vector of those there. All right, and then so your render class is what's going to have your frame buffer, where you're going to update it, set up its shader. That's what the bind is doing anytime that we're using bind. All right. And at this point here in the render function of the renderer, this is a big piece of code here. I haven't really changed anything here. But what I'm doing with my abstraction is when I'm binding to this frame buffer here at line 68, and if you can't read it, it's just whatever's at the top to whatever's at the bottom where I'm unbinding, is now I'm saying anytime that I draw a geometry, if you're drawing your object model or whatever, it's going to be drawn and stored in that first frame buffer. Frame buffer is 0. Okay, and then if I create a second frame buffer, if I want to re-render the scene or do something like that, I could have another frame buffer that I bind to, draw into, collect all the pixel information or whatever the geometry is that's supposed to be output, and have it stored there. Okay, so that's the idea. That's how we're using our abstraction. So at the top, I'm binding to this frame buffer. And at the bottom, I'm unbinding to it. And then anything that happens in between here is getting stored in this particular frame buffer that I've set up here. Okay. Now, by default, OpenGL has always given us one frame buffer, so we've never needed to do this. But now we have the power to create as many as we want. Okay. If you actually look through this code, it's a bunch of GL setup stuff. But eventually down here, you'll see we're actually drawing using our scene graph data structure. From our root, we're calling the draw function here. Okay. So there is actually drawing here, and it's getting all stored into our custom frame buffer. All right. So here's just the here's the magic step then. So here we're at lines, 166 through 107 or so. And then later on in the code, because it can't fit all in one slide, you're going to see I'm not really doing anything very interesting in this OpenGL code. In fact, I'm disabling a bunch of stuff. I'm disabling the depth test. So we don't have a Z buffer anymore. We don't know how far or close anything is, but that's okay. We're clearing our screen. We're clearing all the colors. And then we're switching our shader to whatever our frame buffer object, whatever our abstraction is, to use the frame buffer shader. Okay, so this time we get to use, again, 2 shaders in our programming pipeline. And then I've got this call here called draw FBO, or draw the frame buffer object. And all that's doing is drawing a single quad to the screen and then pasting a texture into it that was captured in this code here, where we were doing our regular draw. Okay. All right. So in today's support code for the lab, what you're going to see is the terrain. Right? It's going to look something like this. But when you actually run it, and if you render the wireframe, this is all you're actually going to see. It's just one quad that's being drawn. Okay, so I'll actually run it just so you believe me. I think it's kind of magic. I don't know. It's kind of an interesting thing here. All right, we can sort of walk around our terrain. Everything looks regular. Then I hit W for the wireframe, right? I'm just doing GL polygon mode like we've been doing before, and it's just a quad. Okay? Because I'm doing essentially 2 passes when I'm rendering. One render of my scene, capture all the data, draw all that data into a separate frame buffer that stores that data in a texture. And then the second pass through, or the second draw call, I'm just drawing a single texture onto this quad here. Yeah,
so
question?
Is that rendered in the goal of the lab today, what we should be getting out? Or?
Yeah, so what you're going to be getting out, so this is what you're going to have to start with, actually. But the cool part is, or again, what I think is the cool part, or the goal here, is now that you're just drawing everything to a texture here. Let's see here. And let me get you to it since you asked here. This is going to be our sort of point here. Our point is that we're going to be able to do some post-processing on these pixels. We're going to be able to do it fast or in real time because fragment shader is very parallel and so on. And the idea of post-processing, and if you haven't seen it, it's taking an image or something that already exists and then modifying it. Right? So if you've ever done, removed red eye or something from a photo, that's post-processing. Most of the time I think of it as something like this, though. where we've got this scene, and then just in one line, this is a really simple fragment shader. You can invert all the colors. Okay, so this one's just saying, okay, whatever the texture color was, subtract 1 from it, and it'll flip all the colors. Okay, so that's kind of interesting. And that would be an example of a post-processing effect that I want you to achieve today. Okay. Now there's a bunch of these different effects that you can try out. And the idea is you're going to be applying a post-processing kernel, which, again, let me sort of illustrate it here. And I'll draw as well. But the idea is, if I have an image here, and I have a bunch of pixels, something like this. If I wanted to apply some effect like a blur to make my image sort of blurry or apply that motion blur effect, I would look at one of these pixels, and then I would look at all of my neighboring pixels around me, and then take the average value and then apply that pixel to me. And then I'd walk over to the next pixel and repeat that process. Okay? So that would be an example of an effect that you can apply today. Some other of the effects that you can apply, things like edge detection. So that would be the second, third, and fourth image here. So if you just want outlines of figures, you can apply something like that. And all you're doing is taking this kernel function here, and you're saying these are sort of the weights of how much of the actual pixel that you want to apply. So the identity is saying, hey, I'm just influencing my current pixel, which is here in the middle, and don't take any influence from the neighboring pixels. Versus if you look at the box blur here, which is an example, saying, hey, if I'm looking at this pixel here, and you're looking at them one at a time, take the average of all the pixels around me, and that's the new pixel color. So that's what gives you a sort of blur effect. Okay, and depending on how you apply these different kernels, like with an edge detection, you can get different effects here. All right, so that's going to be the goal today. To apply one of these kernels in your shader and get a post-processed effect here. All right. All right. Questions about that task? It's kind of a fun one. You can play around with it. You can look at various kernel operations. The Wikipedia has a bunch that's linked here, as well as the Learn OpenGL site actually has a few that are interesting. This would be the very simplest. If you wanted to finish the lab in less than a minute, you could do something like this. I think I actually do have do something more interesting than this, but try this, see the effects, see that it's working, and the sort of power of it. I mean, I think that's pretty cool that you can apply this in 1 second. But think about how you can make it fade or attenuate over time, or do something interesting, or create like an X-ray effect or whatever. Let's see. So here's an example of a blur effect from Learn OpenGL, and that's going to be your lab task. Okay, so there's some example of how you'll apply the actual kernel. So if you're trying to figure out hey, how do I get my neighboring pixel values, here's the idea here. Okay. Here's what it looks like if you do just invert the color. Okay, let me back up just a little bit here, then we'll take a break. Then we're going to do a little activity. But I want to show you some other purposes of the Framebuffer, beyond just like, hey, that's cool with the graphic study. Some different things that you can do with the Framebuffer. Right, since you have total control over how you're rendering your scene. If you've been wondering about one way that you can do selection, to truly make our applications interactive, this is a pretty cool technique. Let me go ahead and click on it here after the commercial. Skip. So the idea that's being shown here is, again, the scene is being rendered twice. The first time you're just getting the scene here. It's a bunch of quads with this airport on it. But the second time that's being rendered, each of the quads that make up the scene are assigned a different color, a unique color, right? Different shades of red. And then what you can do is just test whatever the pixel color is. There's a GL get pixels function that's under your mouse, and then you know exactly which piece of the geometry that you're selecting. Okay, so that's the idea of using a color buffer, right? Just storing colors, rendering that first, capturing what the pixel is where your mouse is, and then you can perform selection. Okay. So here you can actually see where they've drawn this pink quad here. That's where the mouse is. Okay, so that's kind of cool. All right, and again, you have that power because when you have Framebuffer, you can render your scene twice. Now, what's the problem with rendering your scene twice, though? What was that?
Oh, you're rendering it twice. That's like
Yeah.
twice as many computations.
Yep, yeah. The problem is when you're rendering it twice, you're rendering it twice. So yeah, we've halved our performance essentially. Now I guess we're not technically doing all the texturing and stuff, but we roughly shot ourselves in the foot in a sense when it comes to performance. But some simple application like this, or if you're only rendering a few tens of thousands or maybe a few hundred thousand polygons, that's probably fine on a modern machine. Let's see, some other applications here, just to kind of show off, the different passes in each of the screen buffers. I thought this was a nice demo here. Let's see here. So they're showing actually some code, so maybe this will be helpful for you. But each of the different buffers here. Now on the bottom left here, you can see where they're actually doing the edge detection filter here. The edge detection is a actual pass. I mean, here I think they're just showing it as sort of a cool thing that you can do with one of your kernels. But if you actually compose that, that is combine that with another frame, sometimes what folks will do is they'll sort of scale the image on the left, and then that's how you can get objects around, outlines around objects. So if you're selecting things or doing something interesting like that, that would be one way to do it. All right, so you can see the different passes here. All right, and one more example here. After our commercial break here. Come on. There we go. Whoa. Let me just pause it. What's going on here? Play it again here. Can folks tell what's going on? How are we getting this effect here using our frame buffer? Yeah, Jake?
And you see the left-hand side is just a camera of the object, and the right-hand side is that same view projected on the 3D plane.
Yep, you got it. So we're taking whatever we're rendering, since in our frame buffer, remember we create a texture. So whatever our camera's seeing, we have that texture stored in memory, and then we're just going to texture our quad, which is on the right here, with what our camera's seeing. So folks will use this technique if you have a mirror or something in a game and you want a true reflection, or maybe if you're like over water or something, you would render the camera from a different perspective, capture that as a texture, and then render it on an object. So again, this is a really powerful technique to create some of these more advanced, but tend to be more computationally expensive effects. Okay, and in here we are sort of paying the cost of rendering our scene twice here. And we do have to be a little bit careful, but what's kind of interesting about this is, right, in order to get this render, we can't render the object on the right side because it's a mirror. So we need to essentially ignore that in our scene graph the first pass, and then render the texture on our actual object. Okay. All right. Okay, so we've learned a little bit about Framebuffer objects, what they can be used for, and what we're going to do in the lab with applying some post-processing effects here. Any questions before we take a little break? All right. If not, let's break till about 7:13, and then we'll do a quick little activity after that. Hi there. Give me 1 second. I gotta set up our next thing here. Let me just capture you after the break game.
Talk to you about my role in this class. I kind of had to go back on the semester class.
Okay.
I'm back and trying to catch up. Really that far behind.
Okay.
I did turn in my I had my assignment
Okay.
first 3 months.
Okay.
We're here to do that next Thursday.
Okay, let's say you chat after class a little bit. We're gonna get started here. Let's see where you're at and have you emailed me before or? Okay.
Just got back.
Okay. Okay. Yeah, let's have a chat after class so I can just figure out where you're at. Alright, yep, no problem. folks. We're gonna get started here in a sec. Then I'll get you that. Alrighty, folks. Let me get us back in action here, and we'll switch things up a little bit here. So thinking about some of these different graphic studies, had me thinking a little bit about the code that we're writing and the code that you might be writing for your final project. We're getting to the point where, I've written a bunch of support code, we're sort of adding one class at a time and sort of, building our graphics knowledge. The truth is, when I look at the support code, pretty much at the point when I start adding the frame buffers, I'm like, there's got to be a better way to kind of structure this if we really want to start getting into some of the advanced rendering techniques. And start thinking about things like how to handle multiple passes or manage multiple shaders, right? We're missing some things like shader managers or these kind of objects that might make our life a little bit easier. So it's something I think about a lot when designing this course, and how much to give versus not give versus what the abstraction looks like, and if we should just kind of keep piling on. And the truth is, one of the best ways to really learn, what's going on or how some of these components are designed is sometimes to dive in and look at the source code of some larger engines, or see if you can take something away from even their APIs and try to pick out something from their abstractions. Right? We can learn a lot from other folks. So, what I want to do here. Well, maybe first just start with a question here, then we'll get into what we're going to do. Do you buy the sort of frame buffer abstraction that we have? Why bother doing what we're doing? Is it any faster? Is it computationally slower? Do folks buy that it's going to give you something interesting? What do folks think about it? Yeah, Jason.
It's slower computationally, but it gives you more options in terms of effects and
yeah, so we are spending more time, we've got more abstraction. But if we do want to think about something like how would we do edge detection, that's probably a lot harder to figure out, right, if we're just working with geometry. Right, maybe we could do something interesting with rendering lines on top of something, or I don't know. but it does get tricky, right? So we need to have more power. So that's worth having in our arsenal here. So what I want to do is a little breakout activity and give folks a little chance to interact as well with your classmates. For folks who took game engines with me, this will look familiar. In fact, I was deleting some of your old slides for this activity for a few of you who are here. But the goal is going to be to look at some, what I consider high-powered or industrial strength game or graphics engines, just for about 15 or 20 minutes, with some of your classmates, and then add some of your findings to a shared, with our whole class, PowerPoint. So here's what we're going to do. I'm going to divide you up into roughly, I think I've got about 6 or 7 engines, so I'll just grab someone nearby. You can sort of maintain your distance as best as you can. If you're not comfortable, just stay where you're at and then join, a team somehow. But basically, spend, even if it's just 10 minutes looking at, a particular engine. So an example would be the Unreal Engine, or at least just to get you familiar with, if you're interested in graphics, that, these are sort of the state-of-art ones. I want you to look at the engine, figure out, or contribute 1 or 2 key ideas to the engine. In particular, I'm thinking about or looking at the graphics component. So this could be anything like, I see the engine is using a technique called deferred rendering. Or, Unreal 5 is using something really neat with this thing called nanite. And then you can kind of look up what that is. Just see if you can find a few sort of sound bites. Or maybe it's just going to their documentation and seeing what their shaders look like. Or how do they create them. Just some interesting sort of tidbit that you can find here. Okay? So you can figure out, are they implementing some sort of cool graphics pipeline, whatever the case might be. What's their purpose? What's the specialty of a particular graphics engine? Sometimes they specialize in doing animation really well, or crowds, or maybe it's just a general purpose engine that doesn't specialize in anything at all. But that's the idea. And if you would buy it, or if you buy their design, I think it's a good idea. So a few of the engines I've actually picked out for folks are found here. Okay. So this is a shared Google document. I've made a Piazza post here, which I'll ask you to click on. This is actually one of the more fun parts in the class when I watch. Let's see, we've got about 30 or 40 people editing a Google Doc at the same time. So have fun with it. Don't delete other people's slides. But the basic idea is I'm going to ask you to, with a few of your classmates who are around you, take a look at one of these engines here. So I've got a bunch listed. Horde 3D, Ogre 3D, one called Uro 3D, Godot, Panda 3D, Unity 3D, and Unreal Engine. And then just answer, a few of these key questions here. So, what did you look at? Well, that'll be under whatever engine you're using it. What were one or two key ideas regarding the technical component of the engine? Is it using something interesting? Even if you've never heard of that effect or a piece of technology, what's the sort of foundational idea that you can find? Okay. And then if you have any other thoughts about, how did the authors implement it? What's sort of interesting? And then you can sort of comment on, do you think this is a good idea? What's your sort of conclusion about it? Okay. So give folks, about 15 or so minutes to look at the engine and talk with folks and just, throw a few things in the slide. I'm not going to grade you on this in any sort of way. I just want to sort of collectively, give you a chance to look at some of the state of the art in graphics. All right? Does the task make sense, folks? All right. So I'm going to divide folks up roughly into different groups here, and I'm just going to sort of point or wave in your vicinity, and then maybe you can kind of move around. So we'll start with maybe folks, from Ryan down here to work on Horde 3D. Maybe you two gentlemen too. So sort of a team of 5. Everybody up from there. Ogre 3D. And maybe some of you folks can slide over as well. And as soon as, feel free to start moving around and get started. For Urho 3D, maybe not a big group here, the first 2, 3, 4, 5 rows here. The Godot engine, let's see, the 3rd row from the top. How about all of you folks? That's you folks. And then maybe 1 or 2 other folks from the top can join. Yep. Panda 3D for all the folks in the bleachers there. Are we gonna? Let's see, the folks that you want Unreal Engine or Unity? How about Unreal? That one's sort of more. Right. Does everybody have a team? Everybody know where they're going?
Where should I go?
Why don't you join these folks and work on Horde 3D? Feel free, introduce yourself. Say hi to your friends. Yeah, you folks have a. You don't? You join these folks with Unreal Engine.
We're on Horde, and I didn't see a repository for on the Google site. Oh, wait, no, it is. I found a repository. Yeah, they have a link to that. It's on the first page. It's on the where's the website?
Working inspired by the guy. It's in the implementation, so what's been reflected, what's the idea is just and do you buy it?
I mean, it's what?
Is it any good? Yeah.
It sounds like a mobile. There was a game that I was following the rest
I actually really like that. Also, I mean, whether it's physical as well.
Oh, it's this game. Yeah. I've seen it like a meme for it.
It was like one of the biggest PC platformers.
Or one or two kids, the idea of reversing the graphics. In the summary, I'm inclined to just like pull the buzzwords I have on the page down.
I know it's like
Doesn't look like they're posted.
User accessibility over arcade optimization.
Yeah, that's exactly, that's what this, so that they don't have to worry about such,
That photo does have a killer.
I saw these. Kind of, like, yes, exactly. Yes. Especially for someone like you.
20-year-old.
I like those entrances. That's also like this.
I mean,
I'm slowly converting. So it's not like they're gonna like maybe not get something crazy to show up visually, but it's not.
it's like 2 gigabytes. Yeah, exactly.
So what do you guys think are how's the ideas so they can use the camera and just use singing visual at night? What's the
I don't know, if you like to get a couple of kids, I don't know what for example.
Oh, no. Yes, it does. Yes, it does. Like, I thought they were coming up with oh, no, never mind. It does not. It works at screen time.
There's lots of topics that have funny comments. Like even you're just like looking at terrain, like well, it's not. I guess it's not that good. So they have like the whole terrain component that you can make. Automatically displays resolutions for the wind wireframe mode.
Yeah, it does.
Well, this is just an example. I don't know the terrain's like one of the big ones. I mean, they talk about how there's a whole terrain component. Automatically has LOD.
Open source, wood, targets, Mac, Linux, Windows, yeah, I don't think they have anything that's special.
Can we just copy that onto just put it in your own words, yeah? And just use that. We just need to get anything and then just
So that's like after the solution, like new.
That's what this is called.
graphics render is relatively it gives it like the specific I do know this thing.
Oh, it's also over here. Oh, yeah, that's one on top of this one. Yeah, I don't know, maybe that's also
If you're looking for a source, you're right, full featured level, you should check out our own three.
Yeah.
And I think that one is
Reasonable stuff.
I think Framebuffer might be one of the big things. They actually mentioned it more now. There's lots of options.
Shield, mid-caps,
yeah, maybe it's not just that much on it. There would be weird if it's just like, yeah, it would be weird, but also like, to run a game just requires some that's just really,
It's good. I think it does. No.
really strange.
Yeah.
Do you have any idea of the idea of this? I think someone just mentioned about open source to recoder.
I think trying to.
That's like an open source thing.
Yeah, I'm sure it's
I know, it's the open source thing.
Gotcha.
I don't know. I'm just three games that relate to It's been kind of dead since 2015. On the about page, there's a limitation section that doesn't mention those things.
First version was published, 2006. And then technically they didn't get the version until 2017.
Yeah, okay, so I think that's what this is. It's saying that they're doing some sort of computation not just what like objects are visibly from them, but yet maybe objects are walking.
I see that as often as I want to.
So like say you have a
Yeah,
big wall,
that data
for
copy
example,
right here.
there's tons of stuff inside the
I got it
building,
here,
but
but-
you can't see inside.
Update version of application
Things
always
that are inside the
Or
key
do
press
you
stuff.
forums?
And so they're doing this visibility.
Yeah, the actual last quick update seemed to be like 5 years later. Data.
There was a small update last May.
Yeah, otherwise every single time it's like last day, but they were like amazing. Okay, so that's like I'm not sure. I can address this.
Let's just look at the first project.
Let's just try and get some more things down the slides.
We're all hanging out with it.
Yeah. You know. So yeah, I think this is general idea. It's very general purpose. And it's very, like, there's, like, it's supposed to be number one. And I think maybe that's why it's not out of it. Because, like, having that general purpose.
Supposed to be for
Really?
that's what it says for. Like, the end is specific, especially designed for like large crowds. The next camp call.
Where is that?
This is the they say it's somewhere out there.
Because in a review, we're in the shooting, so you can create rooms. University area where only the but then they'll have portals to other windows, doors, where the camera can see into other rooms, but you're not. I mean, everything. It sounds like they're really under the crowds.
Because Unity projects out there.
For what? It's like creating shaders, buffering, whatever. Oh yeah. I think they use a lot of shaders. Right, yeah.
They say it has a shader driven.
It sounds like what I was thinking where it lets you write up your shader. Which is something I mean, like these I think they're just so yeah.
Real time where it's real applications. So I guess it's general purpose.
And it also like it does seem like
That seems like the biggest plus.
yeah, in like a stable environment.
We have an explanation for one of the geometry is optimized for efficient task usage. And supplemented details from all. It's possible to use different scales to apply the third shading to reduce the image draw cost for scenes with many lights.
I mean, you know, it implements some things. Yeah, it implements some stuff to it. It sounds like these things are off doing yourself. If you want.
I think I thought that this was the new flag.
It would be useful.
Look, I thought that this was the new flag.
And that's what they do.
You show off like I don't want 3D.
Yeah. think before that. You probably also try to do yourself. Oh, that's just I don't know, like, if like people can do 3D stuff, if ever not into it. I don't know. Do you want to put that stuff in the slide?
What, like, their explanation for why it's going out?
Well, yeah, does it talk about that? Does it kind of also talk more about how it generally implements? Where's that on the top? It provides implementation for optimization. That's why it wasn't on the top.
I didn't know that. I'm looking for the tree.
I'm just gonna.
Yeah. Is this available?
You folks take a few minutes to pop some things in the slides. It doesn't have to be perfect or professional in any way. It can just be one or two key ideas. Just want to see what folks are learning, then we'll come back together in a few minutes.
We did it?
There's a bug in the engine. Just go fix it.
I think there's yeah, especially when you use the
Oh, really? In the stores?
yeah,
That's so sad.
it's really like
That's probably
that's
probably That's really
yeah.
Is it open source or is it
Just
like
pretty large.
I probably should have huh? Like I totally said it was
I don't know why we just and it's resource ignition is really makes 21. I think I'm kidding.
Actually, I'm like, there's stuff, render video,
You can keep their still lasting, so we can release the version 2.0. Just a thousand contributions to the special Oh, it was gaming. You only need one resource manager. Which one is
so we should probably have this visual server.
yeah, actually, you just need to have
Okay, go for it. I'll give you
it's running in the browser.
That's sick.
I'm not sure how much access to the resources are.
All the theorems.
Alrighty, folks, ready to bring it together? How are we doing? Got enough on the slide? Doesn't have to be perfect. Why don't we bring it together and kind of summarize what we found, or if there's anything interesting or inspirational. Let's see. So I'm just going to kind of go in order. I'll see if anyone from your group wants to talk. Otherwise, I'll just kind of take a peek. I'm familiar with most of these engines too. But why don't we look at Horde 3D? Anybody from the Horde 3D team here want to talk about anything in particular, or should I just kind of flip through?
I mean, I guess the Movie Sugar thing is that it's just generally like a general purpose engine that implements a lot of optimizations for graphics.
Perfect. Yeah, it's actually so. I like what you guys capture. Yeah, there's a Uber shader. Okay. Now, a lot of these engines, that's enough of a key idea or sort of an interesting key term. A lot of these engines will just have one sort of Uber shader where everything's sort of thrown in, like all the code. Usually that's auto-generated, or they have some other tool that's going to help you generate what that actual tool is. So that's kind of interesting. That's an interesting idea. They're using GLSL. A couple other ideas here. I see a lot of sort of advanced level features here. It's actually a pretty nice engine. It's probably one no one's heard of, unless you've taken game engines, because I also put it in there. But it's small enough you could probably learn it within a reasonable time, meaning like looking at the actual source code. It might be good, like supplementary, if you're figuring out like, hey, how should I really make like a good rendering pipeline that's reading in a bunch of shaders and generating this sort of Uber shader thing. Let's see, I'm just going to kind of flip through and just, let's see, the main selling points. What did folks find here? Yeah.
No, I missed my thought. It's supposed to be in Comic Sans.
Yeah, I guess this is the big one, right? It hasn't been updated in 5 years, so so we're probably not buying it. You're probably not doing development in this, but it is a pretty reasonable one if you just want to learn about some graphic stuff, right? There's plenty of stuff we're not touching in this class that this engine has. I did find, I don't know, did your group find any of the documentation where they talk about their actual rendering pipeline? I know. Yeah, I know they do have it. I mean, you're not going to find it in, I gave you like 15 minutes or whatever. But that is one of the sort of interesting. That's my selling point. Now, would you use this? You should probably learn, Unity or Unreal or those. Now, you do have this note that's designed to render large crowds here. So that seems like sort of the selling point or what the original author was developing this for. Let's see. It has some optimizations. All right. Awesome. So yeah, they're trying to, I'm just going to kind of highlight some of this stuff and feel free to dive in, but reducing the number of draw calls that you have. Right, the less times you have to call any function, that's good in general, but of course in OpenGL, since we're sort of switching between CPU and GPU, that's a big thing that you'll hear. So that's a nice thing to kind of capture for us, pragmatically. All right. Any final words on Horde 3D?
5 out of 10.
5 out of 10. We'll do ratings. All right. As you can see, we're just going through this really quick, really informal. Oh yeah, good. And you folks have your names on here. Awesome. All right. Let's do the same experiment, or the same investigation rather, for Ogre 3D. Any key ideas folks want to shout out? Yeah.
Sure. So Ogre 3D is an object-oriented graphics rendering engine. It's meant to be used for graphics of any kind. So you can use it for games, but it can also be used for drawing, business, and a whole list of examples. It's cross-platform. Use it to render for pretty much anything. And it makes use of deferred shading to render as 3D scenes, which has some good optimization benefits, but it makes the graphics pipeline really clunky because it has a very specific way that it needs to be set up.
Yeah.
It also makes rendering transparent objects hard, but apparently they handle that for you, so it's not an issue you have to worry about.
Awesome. Yeah, I like this. Deferred shading. So something we learned about, that's a sale point. Might be worth looking at their API again just to see what do they support? What's the renderer class look like? If you can check that out. So Ogre's actually a pretty good engine that has had some commercial success too. Let me kind of flip through what you folks have here. Okay, yeah, they're using transparency, take care of all these image formats. That's awesome. That's a big feature. We haven't talked about SDL image, but if you do want to load JPEGs or PNGs, we can do those sort of things. And a bunch of singleton managers. Interesting. Okay, so we did find those used in practice. Again, singletons, folks probably in OOD told you never use them, but in games they just pop up a lot because they're really handy, and they're usually the right tool for the right job. Yeah, what do you folks think? You gave it a yes. Does it pass the vibe check? All right. So there might be some implementation, right? We're stuck to their pipeline, I guess, in a sense. So let's see. Score out of 10. What do you folks think?
7, 8 out of 10.
7,
Or
8.
usability.
7 and 8, but maybe loses some for usability. All right, I'll buy it. So some interesting things if we want to look into deferred rendering, right? This is open source. It's object oriented. I would actually recommend taking a look at Ogre in general for the code if you're looking at building model loaders and those kind of things. All right, this one, Urho 3D. Let's see, that is this group right here. Yeah. What do you folks think? Any highlights? Anybody from the team?
So we kind of struggled. We felt like the documentation was a little slim at best. So it was kind of hard to find any like motivating like ideas behind the project. So we pretty much just kind of had to look at the code.
Yeah.
So as far as that goes, I mean the code seems pretty well put together and clean, but small at the same time. So I mean one of the things we saw was the terrain editor, but for the most part it was just kind of like perusing the code base to try to find things that looked interesting because the documentation was slim.
Yeah.
And so we think that would make it kind of hard to learn and use.
Yep.
At least the API I thought was nice at least.
Yeah. Okay. So good API. I recently read that one of the number one things that'll get people to not adopt your projects, if you're building anything open source or going to commercialize anything, is lack of documentation or lack of a showcase of commercial like projects. So I'm wondering, did they have anything beyond the terrain editor that popped out and they said this game was made with, or this game's on Steam and nothing?
Demos of themes that running in the engine. They weren't that quality, but
Yeah.
they don't like
They're
impressive capstones or anything.
Yeah, they're just like basic things, like I just managed to flip this car over, but it's this
Yeah.
little like car thing that drives around.
Yeah. So it does build at least. The engine builds.
Not really a selling point.
Yeah, I mean, well, yeah, I think for this particular project there are like 50 or 60 samples or something in there. The car one being kind of interesting. Let me see what else you folks have here. So yeah, the open source terrain editor. Yeah, but maybe they need to work on their showcase. Has this engine been updated recently?
Yeah, 2 weeks ago.
2 weeks ago. Okay, so that's another sort of selling point. They are updating it. I wonder if they're, you guys are answering my next questions here, they're sort of up to date using Direct 3D11 and sort of the newer APIs. Looks like OpenGL stuff. And the physics engine. Okay, so that's where the car example is coming from.
One thing that we can do is look at Python. It seems like it might be a bunch of that. I don't know.
What was that?
Just when it's written in Python.
Oh, written in Python.
It's just going from C++, like so close to the board, such a high level language, like there is something.
Yeah, performance-wise,
Yeah.
potentially, depending on where you're, hopefully the heavy lifting on all the graphic stuff is, in C++, but there is some, I guess, communication between the language interop where you have to be a little bit careful. Yeah. Let's see. Yeah, that's kind of interesting. The wrapper's just in Python.
It's a third party thing as well. It's not a big project. It's just some guy doing a wrapper in Python for
Oh, I see. Yeah, for the physics engine. Yep.
Yeah,
Interesting. Was there anything interesting? I'm just trying to look. Okay, they're using a scene tree, so that's good. So maybe there's something we can pull out of there if it has some samples, just to see how that's structured. So for folks looking, to do something there, at least it has code. It seems well documented, and some samples of how to use it. Okay, let me get to. Do you guys buy it? What's the rating out of 10? What would you folks say?
It's kind of hard.
Well, if they gave that first one a 5, like, kind of skewed this scales a little bit.
Yeah.
You put Matt out of 10.
I put Matt out of 10 on the slides, but it hasn't shown up.
Oh, all right. Let's see.
Yeah, there it is.
There it is. All right. Our scale.
It seems to just, I'm not sure if it really has any advantages over like other engines.
Sure. Yeah. Yeah. I mean, you get the code. You get to work in pure C++. I'm actually curious what some of the other groups, maybe the Unreal, will say about that, because you're sort of locked into their system. So maybe that's a benefit, right? Maybe this is extensible if you need to refactor it. All right, Team Godot. What do folks think here? Let's see. This group up here, yeah. Summary. Any keynotes you want to highlight? Let me kind of flip through here. Considerably different approach to rendering. Do folks want to talk about that? I actually don't know too much about that other than they're updating it. Yeah.
Yeah, so Godot actually uses, they do all their rendering in a server. So basically it is kind of like you can talk to it via very strict API calls, but you really can't get in between all the layers of rendering and mess with it too much. And this is done so that it's like very like user friendly and for a number of reasons, but it's a little bit like slower, I guess.
Sure.
But they do it for like understandability,
Yeah.
which is like a big part of Godot since it's an open source project.
Right. And I know, I mean, this is an engine that's sort of been gaining traction slowly in a few years. They're saying, it's going to take over Unity or steal some user base from that group because it's very usable. That's a pretty interesting model. I don't actually know too much about that sort of client-server approach.
I haven't seen it before.
Some folks like to think of OpenGL, or they will describe it in sort of the client-server model as well, right? The server sort of being the GPU or the device. So that's sort of interesting. I'll be curious to look at the API. I think that captures your first bullet point: accessibility over, arcane optimizations. Yeah. What does wrapped shaders mean here?
So that's another kind of step towards accessibility. So the language for writing shaders is very close to GLSL, but they actually kind of take away a lot of the low-level things that you would do in GLSL and just make it much more approachable.
Interesting.
And so they actually, when you're writing the shaders, they will wrap that in another class. There's an abstraction on top of their shader language.
Interesting. Yeah, I wonder if they get rid of the stuff like, some of the more annoying stuff like the layout and attributes and maybe those kind of things, or passing in and out. I don't know if folks saw, but in a lot of the engines, if they do have their own custom scripting engine, or you only write your shader just in one file rather than separating it out like we've been doing. In fact, we don't have to separate it out. We could sort of have everything together. It just sort of makes more sense in a pipeline manner. But from a usability manner for, not everybody who's using this studied computer graphics like you folks, right? Let's see. Oh, this is sort of interesting. Uses Vulkan only.
Yeah, they just shifted to that recently. They used to be OpenGL.
Yeah, I know they're making a big shift with their renderer, I guess. Any other thoughts? I'm just kind of skimming through it.
They really just mentioned usability a lot in terms of like making things easy for the developer.
Yeah, pretty well documented engine.
Yeah, very.
Yep. All right. So what's the conclusion? What's the final word from you folks?
If you really care about open source and want an engine that you can dive into and play around with immediately, very good. It makes some sacrifices on performance. So if you're trying to make a huge game or something super performant, maybe it's not the best choice. But for like learning and doing a lot of cool stuff, that seems great.
Yeah, I like this engine, and this is something, again, the point of this study is for you folks to see some of these different architectures. Maybe dive into this one. This one's been open source forever, as you folks have mentioned. I think it was initially one person and somebody part-time. I think they've slowly been bringing on more developers, and it's cool to take a peek in. it's usually easier to figure out what a good abstraction is from somebody else, like what's the proper design, and then you can kind of rip off that abstraction. The truth is, I was talking to somebody at Treyarch Games, which is Activision. Not the best studio in the world for right now, to put it lightly. But anyway, one of their engineers was talking to me, and I was asking a little bit about design and some of these things. And basically, he said, they basically only use arrays and loops, and that's about it. Because anything else, any abstraction on top of that, slows down the game. So, nothing fancy. But it's hard to get to that point until you have a good design, and that's not a very usable tool. Their engine. So yes, what's the rating out of 10? What would folks say?
Open source out of 10.
Open source out of 10. All right, let's take it. A cool looking game there. All right, let's see our Panda 3D team. That's up top here. Key ideas. Anybody want to shout some out? No? I'll shout some out. Platform portability. Written in portable C++. And this one's actually, on the right side, you can see, also using Python. So it sort of wrapped the engine, or the C++ calls into Python. So that makes this one kind of interesting because all the abstractions that you're seeing in Python are basically the C++ classes abstracted out, right? So they have actors, that's essentially your entities. This engine in particular has an interesting sort of model file they call eggs. So if you're thinking more about, we have our 3D models, how would I capture information about animations, or if I wanted multiple sort of files in a scene, this one might be interesting to actually look at. All right, I think just looking at the Python API is pretty interesting to see how you design your C++ classes. All right, so it supports Python debugging, and it's a wrapper around OpenGL. All right, and this is their commercial game, right? For many years ago, I think Disney Toontown, yeah, that's what it is, yeah. What else can I say about this? I believe now it's a project at, I think Carnegie Mellon's taken over this, yeah. So it lives. It's kind of cool. So commercial, Disney project, a couple of commercial games. I think they had a couple other ones like a Pirates of the Caribbean. Yep. Yeah. So I'm kind of surprised it didn't keep getting developed, but now it's in good hands. All right. Unreal Engine, last one here. Any folks want to shout anything out that was interesting? There's a lot in this one. Let me shout out a few things.
It does just about everything. Really big. Tries to do it as fast as possible.
Yeah, I think that's a fair way to summarize it. These days, Unreal or Unity 3D, those are sort of your two go-to options for a general purpose, do everything engine. I will probably post at some point, maybe in Piazza, not to distract you too much, some information about their Nanite talks. They're doing some really interesting rendering stuff as far as allowing you to render millions of polygons in a single frame. I think it's interesting to see, even if you don't understand it all, but I think you'd pick up more than you think on it. So it's pretty cool. Let's see. What else here? Now this I don't know too much about, this Lumen engine here. For global illumination. All right, so they're using the latest and greatest, DirectX 11, 12. I believe they're also using Vulkan, and probably supporting Metal as well. And this nanite representation of meshes is something that you sort of build, or they build in the engine. I think it's part of the tools. You just click like build nanite or something. It sort of sets it up. All right, so it's a generic game engine. Not really optimizing for any particular case. Yep, you have a lot of control here. most AAA, I don't want to say most AAA games, but most AAA companies that are not using their own engine are probably using Unreal to build their stuff. Unity's got a pretty good hold on indie games, but for the most console games and stuff, this is still dominating by far. All right, would you folks buy it? What's a rating out of 10? That makes sense. 9 out of 10, 10 out of 10. Yeah, most job listings, if you look at them, they want Unreal or Unity experience, or the stuff we've been learning, C++, OpenGL, Direct3D. Unity 3D, I was doing this while you guys were. Fair is fair, right? So Unity 3D, probably know about it, but it's C# based engine, supports many platforms. A few years ago, went open source, 2017, so it was kind of interesting. I was just kind of digging through the source. You can see all the different platforms and APIs that it supports there on GitHub. Something kind of cool is their scriptable render pipeline. I actually don't do much Unity 3D really since 2018. I've kind of stopped, and I live in just OpenGL and pure sort of graphics now. But I think this is kind of interesting. Their scriptable render pipeline, again, giving a little bit more creativity, not having to understand a OpenGL state machine or a particular API is kind of nice if you're going to be general purpose. So that's the idea here. And they have two versions of this, sort of a low fidelity and a high fidelity version. So if you're developing for mobile or augmented reality devices, they have a separate render for that versus their sort of where they're pushing more on sort of high detailed stuff to compete with Unreal. They've got these shader graph tools to build the pipelines, which is pretty cool. I think a lot of these other engines, most all these other engines probably have a tool themselves or a third-party tool as well. So here's just some more example source code of their render, if you want to take a look. And I found a particular section here on their vertex attributes, just to see what their meshes have. So the same stuff that we have, position, normal, tangent. So they must be computing the bitangent in the shader color. And then you can have up to 8 textures, it looks like. Blend weight and blend indices for animation. So there we go. We're almost there to Unity standards. And they have a bunch of different rendering targets and a way to do frame buffers, which is what we're doing today. So that's how I wanted to wrap it up. All right. So hopefully this was interesting or a useful exercise. Dig into some code, see what's going on with different abstractions. If not, in particular, today, in the future, do this exercise. Especially if you're, like me and have 50 unfinished projects at a given time, and you're trying to figure out how do I get started. It's fine to look at some other designs, and it kind of clears your head a little bit, right? You get to write stuff down and look at how stuff's actually done in practice. All right, so with that said, thank you for doing that little activity. There's a little in-class activity for you, and we'll transition into lab mode, where you're able to do your post-processing effect on this scene here. So I'll hang around, we'll take some questions down here on the lab or whatever, and we'll see you next week. Otherwise...